Hello, everyone. My name is Nupur Jain. I work for the Intel IPO team as a cloud architect. Today, we're going to talk about Kubernetes load balancing and related network functions that we are trying to offload using P4 to IPU pipeline. To address the increasing performance and security demands of modern data centers, our effort has been to offload network functions to IPU to accelerate and to provide the right isolation. In Kubernetes, service is an abstraction that defines a logical set of pods and a policy to connect to them. They are represented by a cluster IP or virtual IP for the service. Any client connection to a service is load balanced and flow pinned. The cluster expands and contracts depending on the load patterns, thus increasing and decreasing the number of service pods. This picture depicts the kubeproxy behavior of load balancing. This gives an overview of our control plane. We have load balancer functionality expressed in a P4 program. We use PNA compiler that compiles and efficiently maps these tables to hardware resources. It also exposes a user space logical view of tables for the control plane. Our control plane comprises of a CNI and a shim layer that runs P4 runtime, a gRPC client, and does translation from API attribute value pairs to P4 match action table values. The IPU manager runs the gRPC server and uses TDI table APIs to program the rules to the hardware tables. This gives a logical view of our P4 program. The packet on the client pod is applied directional access control rules. We use the 5-tuple hash plus the VIP IP and destination port of the SYN packet to pick an endpoint IP from the VIP pool. This very first packet is also added to flow cache for flow pinning and also for fast pathing the remaining packets of the same connection. Hit on this table increments the directional counters. If pod sits on the same node, the packet is directly forwarded to its endpoint, or else it's routed to the Tanga endpoint of the other node where pod resides. With this, I pass the control over to Vinoth, who's going to do a demo on IPU.
Yeah, thanks, Nupur. So for this demo, we have x86 host with IPU attached to it, and the Kubernetes P4 program is compiled, and the generated binary is loaded in the packet processing pipeline of our IPU. The P4 runtime server is running on top of IPU manager component. P4 runtime server receives the P4 runtime request, and IPU manager translates the P4 runtime request to the hardware configuration. So to create Kubernetes pod environment, we created 4 network namespaces, pod 0 to pod 3. Pod 0 and pod 1 will be running IPF clients, and pod 2 and pod 3 are the service endpoints which will be running IPF server. And these IPF servers are sitting behind the virtual IP or the cluster IP 10.10.100.1. When the clients request to the IPF server using this virtual IP, the load balancing will happen on the IPU, and the request will be forwarded to one of the pod 2 or pod 3, which is behind this virtual IP. I'll start sharing my screen for the demo. So here I have already configured the initial rules for this initial scenario. And the bottom of the screen, this is where P4 runtime server and IPU manager is running. And for the initial scenario of 4 pods, we have 4 pod 0 to pod 3, and each of the pod has a device native interface assigned to it. And we have pod 0, pod 1 here, pod 2, and pod 3. And pod 2 and pod 3 will be starting the IPF server. IPF server is running on the pod local IP, which is 10.3 for pod 2 and 10.4 for pod 3. So now when the IPF client request to this virtual IP, which is 10.10.100.1, the request will be load balanced to port 2 or port 3. So here, port 0 is requesting to the virtual IP 10.10.100.1, and other ports can also request to the same virtual IP, which is 10.10.100.1. Like in the bottom left, I have port 1 requesting to the IPO server on the same virtual IP. As you can see from the port 0, even though the request is sent to the same virtual IP, it went to port 2. And when the request is coming from port 1, it went to port 3. So the load balancing happened on the IPU instead of the typical kubeproxy, which is running on the host in the real Kubernetes deployment case.
Thanks a lot, Vinoth. To conclude, we are seeing large CPU utilization reduction for host CPUs with comparable throughput for node local traffic and increase in throughput for internode traffic. For latency numbers, we would again see a reduction for internode traffic versus for node local traffic, we would actually see increase in latency because of the PCI hops. Our next steps, we're going to publish our performance numbers as well as carry on with our complete data plane offload involving routing and network policies and tunnels, etc. As well as taking the control plane from host to the IPU course. Hopefully this was useful. Thanks a lot.